The pipe assembly is subjected to the force of F. Determine the moment of this force about point A. So here we have a simple cross product problem to find the moment about a point with a given force. So start by defining our find variable. Find is going to be the moment caused by force A, by force at A. So moment by force. Okay, so let's start with a drawing as always. Even though we are giving a coordinate plane and a figure, I still have to draw it to simplify because a lot of information given in this problem right here. I think it's a little bit easier if we simplify it to what we actually need to solve the problem. So the coordinate system, we have x, y, and z right here. We have the origin right here. Instead of having this really complex pipe that's really trying to confuse you in a lot of ways, we can simplify this by creating a position vector from A to C. I guess this is labeled as A, not origin, so label it A. And here we have point C. So if we create a position vector going from A to C, and we'll simply call that R. Okay? So, and then from point C, where we have R as a position vector going to, we have, let's put in green, we have our force vector acting at point C. Okay? And if we take the cross product of these two, it's kind of hard to tell in this 3D plane, but if we imagine a kind of a plane, I guess you could say, between these two vectors, create a plane right there. The cross product, let me find a new color real quick. The cross product will be a third vector. It's very important. This is a vector, not a scalar. It would be a third vector that is perpendicular to that plane created by there. And I guess actually the vector would not be there. It'd be right here. It'd be acting a point right here. But it's still going to be some perpendicular vector to this kind of plane, I guess, that we create here between these two vectors, if that makes any sense. Okay. So let's start by defining position vector R. So probably the hardest part of this problem, in my opinion, is like this defining R. Because the coordinate plane can be very confusing, a lot of different directions, a lot of different vectors. So by looking at the figure right here, we have x, only x component right here should be that first part of the pipe. So x is going to be 0.5 I, and we'll do the units at the end. That's going to be positive, let's go in the positive x direction. And then for the y component right here, we have two sections going in the y direction. It's going to be 0.4 meters and 0.3 meters. So we add those two together, we'll get 0.7 j hat. And also I recommend using the I hat, j hat, and k hat unit vectors to define these. Don't use angle brackets, that's a math thing. We're doing engineering here right now. So, and then that will also be in the positive direction, defined by the coordinate plane right here. And the one position in the z direction is going to be negative 3 meters, 0.3 meters, negative 0.3 k hat direction, and that's going to be in meters. Okay? Perfect. And we're already given our force vector here. So, by definition, we know that the cross product moment caused by F is going to be equal to R. Moment is a vector. Important note that. Be the position vector R cross the force vector. Okay. So, we're going to set up our 3x3 determinant. Equal I hat, j hat, k hat vectors on top, position vector r, 0.5, 0.7, negative 0.3. And we have our force vector, 600, 800, negative 500. And we can factor all these units. They're given in newtons meters, so Newton times meters. Okay? So we're going to use cofactor expansion to solve this one. So very simply, I'm going to take the cross product here. So it's going to be these two quantities multiplied. For the for the I direction, I'm going to be ignoring these two sides. I'm going to take multiply these two values subtracted by the product of these two values. So we're going to be getting 0.7 times negative 500 subtracted by 800 multiplied by negative 0.3. And all of that is going to be in the I hat direction. Let's double check my work. Perfect. Subtracted, this is the definition of cross product, but kind of the explanation behind it is if you add up the row and column the cofactor is in, then you get the sign. And if it's even, it'll be positive. If it's odd, it's gonna be negative. So we know that the I hat vector is in row 1, column 1, so it'll be getting a positive sign out here. That's an even number, 2. But here for the j hat, it's gonna be row 1, column 2, which is gonna be an odd number, so it's gonna have a negative sign in front of it. So again, ignoring the row and column the j hat vector is in, we're gonna get 0.5 times negative 500 minus 600 by negative 0.3. And that's all be in the j hat direction. Set it equal to force. Okay. And we lastly have the k hat direction. So we know that's in row 1, column 3. If we add those together, we get 4. It should be an even number, so we're going to have a positive sign up front. Okay. Again, ignoring the row and column the j hat vector is in, or the k hat vector is in, I should say. We'll be getting 0.5 multiplied by 800 minus 600 multiplied by 0.7. Okay? And that'll be in the k hat direction. And if we plug this all into a calculator, taking into account the directions right here, we should find at the moment due to F should be equal to negative 110 in the I hat direction. Positive 70 in the j hat direction, and negative 20 in the k hat direction. And that's going to be in Newton meters. Perfect. And that is our one quantity that we're looking for right here, this problem. So we answer what the problem's asking for, and we're done.